Hello, this is Chem 112 review for Exam 1. Exam 1 is going to cover Chapter 14 and 15. Chapter 14 is on reaction kinetics and Chapter 15 is on equilibrium. So let me go over first reaction kinetics. Kinetics is rates of reaction. So if a reaction is given, let me give you a reaction and explain to you how we can define rates of reaction. So nitrogen N2 plus H2, then hydrogen giving NH3. So so 1 nitrogen, 3 hydrogen gives me 2 moles of NH3. You can double check the balancing. 2 nitrogen, here also 2 nitrogen, 6 hydrogen, here we have 6 hydrogen. Now if this is the reaction we're going to study, rate can be expressed in 2 ways. Rate in terms of concentration change. The rate in terms of concentration change. That means how rapidly concentrations are changing. In this case, how rapidly nitrogen is dissipating, hydrogen is dissipating, or how rapidly NH3 is being formed in the reaction. In any chemical reaction, reactants are used up and products are being formed. So that's why we use the word dissipation for reactant, formation for products. So I can write down rate in terms of concentration change. In case of nitrogen, the rate, if I write down rate in terms of nitrogen, it would be like this. Rate equals to minus delta means change, in nitrogen concentration divided by delta T. That means change in concentration of nitrogen per unit time. This is time. And why there is a negative? This is decreasing. Nitrogen is used up in the reaction. When something is decreasing, the change is going to be negative. Think about anything. If you have initial value is greater than the final, then if you subtract them, final minus initial, you'd have a negative sign. So from calculus or math, you also know about it. When something is decreasing, the change is going to be negative. So whenever you see a change, whenever you see a negative sign, that means that concentration is decreasing. Like in this case, nitrogen concentration is decreasing. And this is how I write down rate in terms of concentration change of nitrogen. I can also write down rate in terms of concentration change of hydrogen. So change in concentration of hydrogen per unit time. Or I can also write down rate in terms of concentration change of ammonia. This time it will be positive because it's being formed. That means as time goes on, this is going to increase, not decrease. NH3 over delta T. So I wrote down 3 rates. So keep something in mind. For each chemical species, there will be 1 rate. It's like if there are 3 joggers jogging, for each jogger there will be 1 rate. So they're all changing in concentration with time. Now I can compare these with your jogging rate. If somebody is jogging from point A to point B, how are we going to get the rate? Change in position from A to B divided by time. Say this is 2 miles and say time is 1 hour. So be 2 over 1. So 2 miles per hour is the rate. Similarly, in case of a chemical reaction, concentration change per unit time will tell you the rate. So concentrations are expressed in molarity or moles per liter. So the unit is going to be molarity per second. Here we don't use per hour, so in case of rates, it's per second. So this is, capital M stands for moles per liter. So moles per liter per second will give you the rate of reaction. Now let's go over this more carefully. Now I have three rates because of the fact I have three different chemical species changing in concentration at the same time. Often we have this question in exam, how are these three rates related to each other? And that's what we're going to show you next. I assigned some homework problems. By doing those homework, you'll find out how these problems are done. And I'm trying to explain this to you. Rate due to, let's now write down as if all the rates are equal. Minus delta, change in concentration of nitrogen by delta T, that's the rate due to nitrogen, equals to minus delta H2 by delta T, that's the rate due to hydrogen dissipation, equals to rate due to ammonia. The question is, are they really the same? Answer is no. Look at here. Each time one nitrogen reacts, three of the hydrogen would react at the same time. So these numbers are not same. 3 times more hydrogen will be reacting at the same time, and 2 moles of NH3 will be formed. So rates are not same. Some of these are disappearing faster than the others, if you consider the same time frame. So how do I know that then? How do I set them equal? Well, if I know that this is 3 times larger, to make it equal to nitrogen, I'll have to take 1/3 of that. So now, if I take 1/3 of hydrogen rate, so this is the rate due to hydrogen, let's have 1/3, that will be equal to that of nitrogen. What about ammonia? Ammonia is being formed 2 times faster than nitrogen. So that means in order to set it equal to that of nitrogen, I'll have to take half of that value. Think it this way. If I were to write down these numbers, 5, in one case is 5, in another case 4, if I set them equal, you know that it's not right. How can I make them equal? 5 divided by 5, 4 divided by 4. And these are the coefficients. So here, coefficients of nitrogen, this is 1. So 1 divided by 1, that's equal to 1 divided by 3. So it will be 1 over the coefficient. So keep that in mind. So 1 over the coefficient for the third one. That would set them equal. So what we learned here is rate of reaction in terms of concentration change and how they're related. And you would expect questions like these in exam. So make sure you do some problems on these. Now let's use a few numbers so that we know how to do problems like these. Let's assume that nitrogen is disappearing. This value is given. 5.0 moles per second. Let's assume that in this reaction, nitrogen is disappearing at the rate of 5.0 moles per second. That means every second, 5 of the moles of nitrogen is reacting with hydrogen and giving ammonia. So that's the disappearance rate of nitrogen. Now the question is, if I know that, how would I calculate? So if I know this rate, how can I calculate rate of disappearance of hydrogen? Question like this would be on the test and also in homework problem. I mean, you should do some of those problems. So if I know that nitrogen is disappearing at the rate of 5.0 moles per second. How can I get rate of disappearance of hydrogen? We already know the relationship. This is the relationship we are going to use between disappearance of nitrogen and disappearance of hydrogen. You need 1/3 here. So how can I do this setup? Just write down the way it is. Delta N2 over delta T equals to minus 1/3 delta H2 over delta T. Now since this value is given, so I'm just going to use that number, 5.0. I can ignore now negative. Negative only tells us that it's disappearing. That's what it tells you. So I can cancel out the negatives. So I have 5.0 equals to 1/3 delta H2 over delta T. So the rate will be given by I'm just going by the positive number, but the meaning should not get changed. It's the disappearance of hydrogen, so that's 15. Okay? This would be mole per second. And if you want to assign negative sign, that's fine. You can say negative here, but if you want to write down as a positive number, make sure you write down. This is the rate at which hydrogen disappears per second. I have assigned a number of other problems, and make sure you try to go over them. Often we ask this question, which of these species appear or disappear fastest? This is a qualitative question. You can just by looking at it, you should be able to answer. Hydrogen is disappearing at the rate of 1. Let's assume that all the changes are happening per second. In 1 second, if 1 nitrogen disappears means reacts. 3 hydrogen has to react, because otherwise the reaction is not going to happen. So these numbers, we call it stoichiometric ratios, would remain unchanged. In any chemical reaction, those numbers would remain unchanged. So by the time 1 of nitrogen reacts, 3 of hydrogen would react, and 2 of ammonia would be formed at the same time. So basically, the more being used up means faster is the rate. So in this case, hydrogen is disappearing 3 times faster, so this is fastest, then this, and then this. So sometimes I ask you this kind of questions to see whether you understand the rates of disappearance and rates of appearances of different compounds. So this is about the rate of reaction in terms of concentration change, and I've shown you how these rates are related to each other, and make sure you go over this carefully and to understand it. Now I'm going to show you the second rate expression. So the rate that we just discussed is comparable to the rate of jogging, for example, rate at which somebody is walking, distance divided by time. But now the next rate expression that I'm going to discuss that deals with concentration of reactants. So again, let's go back to the same reaction. Rate in terms of concentration, not concentration change anymore, concentration of reactants. Before we go over any problem, let me try to give you the understanding. Rate in terms of concentration of reactants. Let's assume that I have a big container. That container has the reactants, and I can consider, let's assume a simple reaction, H2 plus Cl2 giving 2HCl. So is a balanced reaction. Say these are H2, the tiny ones are H2, and the bigger ones are Cl2. So these are H2, H2, Cl2. Now let's assume that this box is like a whole room, and I have 2 H2 and 1 Cl2. In order to react, they will have to come close to each other. It's like shaking hands. Unless they come close to each other, they can't make HCl. So if one H is far away from each other, one H is quite a distant from a Cl2, there will be no reaction. Now, if I keep on increasing hydrogen, what would you think? Would there be greater possibility of reaction? Answer is yes. Because now there is a greater likelihood that H2 would be coming in contact with Cl2 and reaction would happen. So as I increase the number of hydrogen, the rate would go up. So this is reactant concentration. If I increase the reactant concentration, there is a greater rate of collision. Because keep in mind, in the gas phase, they're moving at random. So there is a chance that they're going to collide with each other. Now, so as I increase hydrogen concentration, the rate would go up. What would happen if I increase Cl2 concentrations? Instead of having 1 Cl2, let's assume that I have 100 Cl2 in the same space. So a lot of these Cl2. So there will be now greater chance even if you increase Cl2. So it doesn't matter whether you increase H2 or the Cl2. In each case, the collision is going to be more often when you increase the number, so rate of reaction would increase. So no matter whether you increase concentration of hydrogen or concentration of Cl2, the rate of reaction is going to increase. So now we can write down the rate expression by considering that fact. A constant, we call it rate constant, times the concentration of hydrogen, in this case, the reactant, raised to the power, what we call order of reaction, order, and Cl2 concentration, raised to the power B, that's also called order of reaction. So that incorporates what we just discussed. As I increase concentration of hydrogen, the rate is going to increase. As I increase concentration of chlorine, rate is going to increase because there is a greater chance of collision. So this is how we come up with this expression of rate. A constant, rate constant, times the concentrations of reactants and raised to the power numbers. Orders are nothing but numbers. Somebody has to do the experiment to provide the orders of the reactions. That number could be integral values like 1, 2, 3, could be fractional values. But that has to be given to you when you're calculating rate. So if I know concentration of hydrogen or Cl2, value for A, B, and K, I can calculate rate. So this is rate expression in terms of concentrations of reactants. Now let's do one sample problem that uses these rate expressions, and I'm going to use this reaction. Let's change the reaction now. 2NO plus 2H2 and 2 gas plus 2H2O gas. Okay. Some information has to be given. Say we said that this is first order in H2. So let's write down first order in H2. So A equals to 1 according to this information given. Second order in NO. So let's call NO is B. I think we should write down, this is H2, and then this is B, NO, for a different reaction. Okay? Because here we are looking at a different reaction, H2 and NO reaction, raised to the power A, and they're giving you that order is 1. And for B, for order with respect to NO, they're telling that this is second order, so B equals to 2. So basically these are the exponents, raised to the power 1 here, raised to the power 2. So now the rate law, or rate expression that I'm going to write down would be given by rate constant times hydrogen raised to the power 1, NO raised to the power 2. This is often called rate law, because if I know the rate constant value for any of these concentrations, I calculate the rate value. Okay? So this is often called rate law. I think in one of the homework problems you are supposed to calculate rate law. Okay, now let's use some numbers. That way we can do a problem. So let's assume that K equals to, rate constant, equals to 3.0 times 10 to the power 4. 3.0 times 10 to the power 4. Molarity per molarity square per second. That's the unit of K. And the concentrations of H2 and NO2, concentration of NO equals to 0.025 molar, and concentration of hydrogen is 0.020. Okay? So with this given information, how can you calculate rate? So this is the question. So a reaction like this is given, and the question is, when rate of this reaction is first order in hydrogen, second order in NO, and the concentration of hydrogen is 0.020, NO is 0.025, and rate constant has this value, you need to calculate rate. So basically, I need to use this expression. And all the numbers are given. Rate constant is given, so it would be 3.0 times 10 to the power 4 molarity per molarity square per second times hydrogen concentration, which is 0.020 molar, and then NO concentration is 0.025 molar squared because of this square. And that should give you the final answer to the rate. So this is a straightforward question, but question like this would be on the test. Now I'm going to give you another example. So this is our example number 3. Let's assume that reactant is A, giving products. And this could be like N2O5 giving NO2 plus O2. Let me write down as an example so that you don't get confused. It could be N2O5 giving 2NO2 plus half moles of O2. So in general, we often write down in terms of A and B. That should not make any difference. So rather than writing down a specific reaction, we can write down reactant A giving products. So I can give you something like this and give you the rate constant value of 2.0, say this is 2.0 times 10 to the negative 4 per second. And I'm saying that this is first order in A. And you need to calculate half-life. Half-life is the time when the concentration of reactant reduces to 1/2 of its original value. For first order reaction, you'd find in the book there is an expression which is given by 0.693 over K. So it's pretty straightforward. For first order reaction, half-life, this is the time when the concentration becomes 1/2. That means if I start with 2 moles per liter of A, it becomes 1 mole per liter after half-life. And how we get that value? Just by plugging in your number in here. 0.693 over K is 2.0 times 10 to the negative 4 per second. So my final answer is in seconds. For a second order reaction, the expression is different. You do not need to memorize these. You can always find these expressions and can just apply them. But make sure you understand what half-life is and how we can calculate half-life. The next problem that I'd like to go over deals with activation energy. So let me write down here rate, constants, and activation energy. We already know what rate constant is. Those are the small k values. Activation energy we haven't defined yet, so let me go over that. Reactant, product. Let me give you an understanding before I go over the problem. This paper that I'm holding has lots of carbon and hydrogen because it's coming from plants, and plants is an organic substance which are predominantly which has carbon and hydrogen and a little bit of hydrogen and oxygen and nitrogen. And we all know that carbon and hydrogen, when it reacts with oxygen, carbon would give you carbon dioxide, hydrogen would give you H2O. That's a well-known reaction. So basically, when I'm heating this paper, if I keep on heating it, at some point we all can understand that it's going to catch fire. What is fire? That's the beginning of the reaction with oxygen. And that will give you these two products. Now the question is, we have so many carbon, so many hydrogen in this paper. How come it doesn't react at room temperature? Because we have plenty of oxygen. And same is the case I can say about our cell. Our cell has a lot of carbon, a lot of hydrogen, but we exist at room temperature. So why this paper exists? Why it doesn't give you this reaction? The answer would be quite simple. It doesn't have enough energy, and that energy is called activation energy. So reactors just can't give you products. You'll have to provide minimum energy. So minimum energy needed for a reaction is called activation energy. Quite often, we ask you to calculate activation energy, or we'll give you activation energy and you need to calculate rate constants. So let me give you that expression. In the book, you'd see that expression too, and you can use it. Log of this is natural law, K1 by K2 equals to activation energy over R times inverse of T2 minus inverse of T1. Now let me define these. T1 and T2 are the temperatures. So K1 is rate constant at temperature T1 degree Kelvin. These are all Kelvin. Even the question gives you temperature in degree centigrade. Make sure you change it to Kelvin by adding 273. K2 represents rate constant at temperature T2, and that also has to be in Kelvin. So let's put down the unit. Not to be confused, let's put down degree Kelvin. Normally we don't write down degree Kelvin, but just to not to get confused between rate constant and Kelvin. Okay, so K1 is the rate constant at T1, K2 is the rate constant at T2, and these are functions of temperature. Rate constants are functions of temperature. So now I have these values. Now I just need to have constant R. So R value. Now in book you'd see two different R values. One R value has atmospheric unit, liter atmosphere per degree per mole. The other R value has unit of energy, which is joule. And in this case, we're dealing with energy, activation energy. So I must pick the R value with unit of energy, which is 8.314 joule per Kelvin per mole. So that's the R value you're going to use in solving this problem. And for doing this problem, I need additional information. Let's assume that, so what is given? Activation energy says given, which is 32.0 kilojoule per mole. Say K1 is given at 25 degrees centigrade, and which is 2.0 times 10 to the negative 2 per second. And obviously my temperature 1 that goes with K1 would be 25 plus 273. So that's how you get Kelvin value. And the question is, what is the K2 value? What is the K2 value at 90 degrees centigrade? And temperature 2 obviously is 90 degrees. So it would be 90 plus 273 Kelvin. Well, how do I do this? Plug in your numbers in this expression. Let's do it. Log of K1, which is 2.0 times 10 to the negative 2. K2, we need to figure out. So that's at the bottom. EA, which is 32.0. Always develop the habit of writing down the units. That we know if we made any mistakes. This is kilojoule per mole. And that's EA value. R is 8.314. And that's joule per Kelvin per mole. And this is kilojoule per mole. Right away you see that there is a problem with the unit. You have a joule, kilojoule. So I will change it to joule. So multiply it by 1,000. 1,000 joule makes a kilojoule. So I'll write down 32.0 times 10 cubed. Or times 1,000. That will give you joule per mole. So that would give you this value, EA over R. So this is EA, or activation energy. This is the R value. Inverse of T2, I mean we already talked about this T2, 90 plus 273. So plug in that number here, inverse of T1, and plug in. And then you need to first get the right hand side value, and then take inverse of log, this is base E. And then from there you can calculate K2. So I'm assuming that you know this algebra. At least you need to know how to use your calculator, because we'd have this kind of question in exams. So read the manual of your calculator so that you know how do I go from log to inverse of log, so that log would be gone from here, and then it would be just like a simple algebra setting. So I strongly suggest that you learn how to do problems like these. So because I know all the values here, so I can calculate the right hand side, and then I would get rid of ln by taking inverse log of the values. Next, I'll go over another example where we're going to define K equilibrium, Kc, and Kp. Now, what is equilibrium? So let me first explain what is equilibrium. Equilibrium, Kp, and Kc. Let's go over a particular reaction. 2NO. Let's assume that they're all in gas phases. So at this time, we're not dealing with heterogeneous. They're all homogeneous. Plus 2 hydrogen, giving nitrogen plus 2 H2O. Now let me first explain to you the equilibrium concept. Say at the beginning, I'm just adding nitrogen and hydrogen together in a container, and I provided enough energy so that they can react, and they will start giving products. So as this reaction happens, we are getting more and more nitrogen and more of H2O. Question is, can you get these products forever? Answer is no. After some time, some of these products react backward. So that's going to go back to this reactants. So in other words, as you wait long enough, the rate at which products are being formed at the same rate, products would break down and make reactants. And that's called equilibrium. Quite often students get confused. By equilibrium they would mean overall nothing left. But truly that's not the case. Let me give you a simple example of equilibrium. Say at the beginning of your class, imagine you're in a classroom. You're the first one to get in. And as time goes on, the second student comes in, then third student comes in. That's like gradually forming products. So after some time, let's imagine that after some time, 10 of you came in the class. So 10 of you in the class. After 1 hour, one person goes out and one person comes in. So we have 10 students in the class. After 1 hour, one person steps out. At the same time, another person comes in. What would be the number of people in that classroom? It's 10. So that number is not changing even though something is happening. What is happening? There's two rates of motion are going on. One is going out, another is coming in. That's how equilibrium happens. As you wait long enough, if one molecule of reactant breaks down into products, one molecule of product would go back to reactants. So it would seem to you as if nothing is happening, even though these are happening at the same rate. Just like one person goes out, one person comes in, can happen at the same time. So at equilibrium, concentrations remain unchanged. So before you reach equilibrium, concentrations will keep on changing. After you reach equilibrium, concentrations do not change because forward rate equals to the reverse rate, and they're going to balance each other. Which is same as saying that one person is going out, another person is coming in at the same time. So one of the criterion of equilibrium is forward reaction rate equals to reverse reaction rate. So this rate is equal to this rate after that time. But at the very beginning, you don't have that. At the beginning, product will be built much faster. After some time, the reverse reaction is going to happen. Now, when equilibrium is reached, concentration of NO is going to be fixed, H2 will be fixed, N2 will be fixed, H2 will be fixed. And we'd call them equilibrium concentrations. So this is the symbol we're going to use for that. NO, equilibrium concentrations. EQ means equilibrium concentrations. It's not same as initial concentration or the concentration you started with, because your initial concentration would keep on changing. Initially, it would keep on changing, it would give you products, and finally, there'd be no more changes in concentration at equilibrium, and that's the concentration, which is called equilibrium concentration. So don't be confused between equilibrium concentration and initial or added concentration. Equilibrium concentration you can think as concentration at the end, not at the beginning. And this concentration remains unchanged. Once you reach equilibrium, you can write down an expression, what we call equilibrium constant. So K equilibrium is called equilibrium constant. Now how do I write down that expression? If this is the reaction we're looking at, product concentrations on the top, raised to the power, coefficient of the balanced reaction is 1. Raised to the power 2, that's the coefficient of the balanced reaction, divide by NO concentration, raised to the power 2. Again, this is the number. Hydrogen, raised to the power 2. Coefficients of balanced reaction. And this is called equilibrium constant. So let me double check. Products on the top, reactants on the bottom, N2 raised to the power 1, H2 raised to the power 2, NO2, H2, 2. And equilibrium constant, you can see that this is the constant as long as temperature is constant. So in book, they often write down different constant values at different temperatures. So you'll have to know those, you'll have to know how to use those values. Here I want to point out to you, if equilibrium concentration is large, if this is large, by large I mean say 10 to the power 10, for example, 10 to the power 5. That means I have high concentration of products. High product concentration. Because my top number has to be large in order to give such a large value. If equilibrium constant is small, so 10 to the negative 3, negative to the 4, negative 5, negative 10, those are small values, that means reverse is the case. Reactant concentration would be large. Okay? So then in other words, if you're doing an experiment, if you find that equilibrium constant value is quite large, that means you're going to get high percent of products. So these are some of the things you need to understand. Now, let's do one specific problem so that we can apply this. And before I do that, I must tell you the equilibrium constant can be expressed as Kc in terms of concentration units in molarity units. So that means if I have nitrogen concentration in moles per liter, hydrogen in moles per liter, then it will be called Kc. C for concentration unit, which is molarity. Kp is pressure unit in atmosphere unit. And how Kp and Kc are related? We often ask that question. Kp equals to Kc RT to the power delta N. Delta N means change in the number of reactants and products as you go from reactant side to the product side. Let me show you for this particular reaction what would be the delta N value. Delta N would be number of products. For this reaction, I have 2 H2O and 1 nitrogen, so there will be 3 products, minus 2 NO and 2 H2, 4 reactants. So, raise to the power minus 1. So I can now write down for this expression, this reaction, I can write down Kp equals to Kc RT to the power minus 1. Then you can plug in these numbers. R is a constant value, T is temperature in Kelvin, and Kc is known, then you can calculate Kp. So make sure you do calculations like these, Kp to Kc. And by the way, if you're looking for the R value, as I say, R has 2 different values depending upon which unit you're going to select. For this kind of problems, you need to use this value, 0.0821 liter atmosphere per degree Kelvin per mole, not the joule unit. And this would be the straightforward answer to this question. Now we're going to do another problem that will deal with calculation of equilibrium concentrations. Now let's keep the reaction same. So before I go over the next type of problem, I must remind you this. Kc is the equilibrium constant in molarity units or concentration units, Kp in atmospheric units, and this is the relationship between Kp and Kc. For this particular reaction, I got delta N equals to minus 1. So 2 plus 1, 3, that's this 3. 2 plus 2, that's 4, that's minus 4, that gives you power of minus 1. Let's now do equilibrium concentration calculation. Let me remind you again, equilibrium concentration is the concentration that you get at the end when equilibrium is reached, when there is no more change in concentrations, as if reaction is not happening. The 2-NO concentration is 1.00 molar. Hydrogen concentration is 1.50. These are all initial values. So the wording of the question would be, you're going to add 1 molar NO to 1.50 molar hydrogen. And initially, if there's no mention about nitrogen, that means no nitrogen at the beginning. Let's call it 0 molar. Because in book, when they don't say anything, you can assume amount of nitrogen to be 0. And in case of H2O, say 0.15 molar. So we know that initially that's all that we have. Now we're saying that at equilibrium, that means you let it react. When it reaches equilibrium, the concentration of NO, so let's put down NO equilibrium, equals to 0.032 molar. With this information, I would like you to calculate equilibrium concentration of hydrogen, nitrogen, and H2O. Remember equilibrium concentration? The concentration that's going to exist at the end after equilibrium is reached. We know the initial concentration, but not the final. Let me show you how we can find it out. I know the initial concentration of NO is 1, but final NO concentration is less. Now why it is less? Because some of this NO has reacted. So how much of NO has reacted or used up? So let's write down that. NO reacted or used up. You can write down either way. How much NO is reacted? Initially we had 1.00 minus 0.032. So that would give me 0.962. 962. I just want to show you some of the numbers. That's how much NO would be reacted or used up. Whenever something reacts, it's be used up. So both would be alright. So let's put down used up for the time being. Used up. Because we use it more often than reacted. Now if this much of NO is used up, question is how much of hydrogen will be used up? Let's try to understand that. Chemical reaction tells us when one of the reactants is used up, how much of the other one will be used up and how much of the products will be formed. Now this is how you'd be answering this. Let's try to understand the reaction here. This reaction tells us that when 2 moles of NO is used up, 2 moles of hydrogen will be used up at the same time. Otherwise, this reaction cannot happen. This is, remember I was telling you about this stoichiometric ratio, and it has to maintain that ratio. So 2 of this would react with 2 of this, and is going to make 1 of the nitrogen and 2 of H2O. And that has to be maintained. So, if I know how much NO is used up instead of 2, I'm saying that 0.962 is used up. How much of hydrogen will be used up? It will be the same number. You can see 2 and 2, so 0.962 is used up for NO. That means 0.962 would be used up of hydrogen. So let's write down that. 0.962 molar of hydrogen used up. Now, if I know how much hydrogen is used up, I can find out from here final concentration of hydrogens. But let me now find out how much nitrogen is formed. Remember, products are being formed, reactants are used up. So, NO formed. This is used up, this is formed. 2 and 1. So that means it becomes half of this number. So we know that NO used up is 0.962. Half of that would be for nitrogen. It would be half times 0.962, and that's going to be 0.481 nitrogen formed. And concentration of H2O formed, I'm running out of space here. It will be the same number, 2, 2, 2. So it's going to be 0.962. So now, I got all these values which I can use for equilibrium concentration calculation. Now let's calculate now equilibrium concentration. I already know the NO value, which is given. So let's repeat that. NO at equilibrium equals to 0.032 molar. Hydrogen at equilibrium. This is how we should be thinking. This much of hydrogen is used up. How much we had to begin with? We had 1.50. So out of 1.50, this much was used up. So the leftover is equilibrium concentration. But that's going to be left. 1.50 minus 0.962, and that gives you, for hydrogen, that would be 0.532. make sure you do this problem independently. First you learn how I'm doing it. What about nitrogen in equilibrium? Concentration of nitrogen in equilibrium. Again, initial concentration, I had nothing. 0 at the beginning. Since this is a product, it's going to build up. How much was built up? Nitrogen formed 0.482, so that's going to be added. So answer is 0.481 molar. That's for nitrogen at equilibrium. And H2O at equilibrium. Again, this is the product being formed. How much we had at the beginning? 0.15. So this is the initial value, plus how much was the built up because of the reaction. Water being formed is 0.962. So that needs to be added. Here you need to pay attention that the reactants will be consumed and product will be formed. So when you add up all these, it's going to give you 1.11 molar concentration of H2O. Now, once we know all these values, now the question could be given in several different ways. I can either ask you to write down equilibrium concentrations, or I can ask you to calculate Kc value. For Kc value, you're going to use numbers like this: N2 at equilibrium raised to the power 1, H2O at equilibrium raised to the power 2, because these are the coefficients, NO at equilibrium raised to the power 2, H2 at equilibrium raised to the power 2. So basically you plug in your numbers, and these are the numbers. So just plug in, and that will give you the final answer of Kc, if the question is also asking for Kc value.